So, Professor Suzuki,
Yes.
you are one of the founders of the famous Super Kamiokande experiment, and first of all, I would like to congratulate you to be awarded recently by the European Physics Society
Thank you very
for
much.
your outstanding contribution to neutrino physics. And now, could you please comment on the most exciting and important results have been obtained by your experiment and about your future plans?
Okay, so our most important result is the discovery of the neutrino oscillation in studying the atmospheric neutrinos. But not only that, and we also made a significant contribution for discovering solar neutrino and oscillations with SNOW experiment in Canada, and also our Super Kamiokande detector is used as a far detector of the long baseline experiment, first in the K2K, which confirmed the atmospheric neutrino oscillation, and next in T2K, which shoot the neutrino from 295 kilometers far from the detector. And then we made the first indication of the non-negligible theta 1,3.
And
So
about the future,
yeah.
what do you plan?
Yeah, future, and we are planning to make a bigger detector, about 25 times the current Super K, and then there are a kind of unknown problems and remained in the neutrino science. For example, we have to determine the mass hierarchy, and there may be a small violation of CP in neutrino sector. That's a kind of very interesting the subject in our future. So Hyper Kamiokande, and if built, and can attack those kind of things.
So you claim very exciting and very important for fundamental knowledge about the nature program.
Yeah,
I
that's
would like
right.
to wish success.
Thank you very much.
Thank you for coming for the Lomonosov conference. It is a great honor for us.
Thank you very much.
Bye. Well, it is a great honor and pleasure for us that two distinguished particle cosmologists are participating in the 16th Lomonosov conference on elementary particle physics. And I would like to ask you one question to both of you, to Professor Di Bari and Professor von Nenger from Italy and England.
University of
from Torino. Yeah. Well, we have just now witnessed a very important and exciting period in the history of particle physics in general. Just this year, we have got a solid confirmation that last year and this year we have got a solid confirmation that really Higgs boson exists. It was the discovery at LHC, and just in the talks on the conference we get once again confirmation that it is true. In addition, and this has really put a standard model of particle physics on a solid basis. In addition, during recent years we have observed in many experiments in neutrino physics that the famous and one of the important mixing angles, theta 1,3, is really not zero. It opens a room to really new physics. And I would like to ask you, like the world famous expert in the field, what frontiers these two discoveries open to cosmology and particle physics and cosmology? Could you just think about this and answer this question?
Yeah.
So actually these discoveries have actually been very, very important. So we have now almost complete confirmation of the neutrino sector of the standard model. We are just basically fixing all the mass intervals and the mixing angles. And from the other side, more on the general side of particle physics, the standard model is basically confirmed to a very good level of precision. So the next point is moving forward to understand some very important and not completely understood for the moment solutions for actually something that comes from a different side, but it's related to particle physics, which is actually astroparticle physics and cosmology, where we have basically important unknowns at the moment. One is actually dark matter understanding, and this is strongly related to what you were saying. We have the fact that the universe is made by baryons and not antibaryons, so particles and not antiparticles, and Pasquale will say definitely more, he's leading expert in that. So the baryon asymmetry, and obviously also dark energy, but this is an even maybe farther point. So from my point of view, my expertise, the important thing is that now the standard model is fixed, but this is not enough to explain dark matter, because dark matter now it's clearly understood that we need something more which is from particle physics side. And we can look at many astrophysical and cosmological probes for that. So now we understood how the basic and important particle physics sector is done, and now we have set the basis for next level, and the Higgs discovery is actually fixing one parameter we were missing, actually the mass. To some extent the couplings are actually coming out now, and so we could start from that to understand what is the direction. And there are many ideas, as we had in the last years, but this can be supersymmetry or can be just more simple but more specific models that could explain dark matter. And at the same time, the neutrino sector, which is much more related to, in cosmology, to actually what Pasquale is doing, on the leptogenesis and baryogenesis, neutrino sector can be linked to the dark matter problem, especially in some specific models where we could have, for instance, in supersymmetry, we could have a connection between the two sectors, neutrinos and dark matter, because supersymmetry could link the two sectors in this way. Neutrinos have a scalar particles, superpartners, which could be the dark matter. So solution in one sector could be induce information on the other sector, and people is actually working on that. Even though up to now the more specific supersymmetric model we're not thinking about that direction, actually people have started to do that, and there may be interesting connections.
Well, thank you. And
yeah, you mentioned the discovery of the reactor mixing angle, and I would say that the Higgs boson marked a huge discovery in fundamental physics, and it somehow confirmed the standard model, closing, however, a stage that was lasting the last 45 years. But with the discovery of the reactor mixing angle, it directly points to something that we already been knowing since 10 years, 15 years, that is neutrino oscillation. But experimental is very important because having a non-vanishing θ13, as we have learned during these days, it opens the door to measure also the other unknown parameters in the leptonic mixing matrix, like such CP violation, mass ordering, and also better measurement of the atmospheric mixing angle. So we will have probably in 5-6 years very important information in the neutrino sector. And what we miss, and that is very interesting, is a model where all these pieces of information all fall combined together. And from that point of view, I think that the idea of explaining the matter-antimatter symmetry with neutrinos is really fascinating, and realizes the dream of Andrei Sakharov, that 45 years ago he was thinking that the CP violation could be linked to the mystery of the matter-antimatter asymmetry of the universe. And the leptogenesis does exactly that, but through a specific realization within neutrino physics. So it could be that in the next years, when all these numbers will become more precisely accurate, maybe some model, some new theory will emerge that will go beyond the standard model, that where, however, the Higgs mechanism still has a huge importance. For in leptogenesis, we need the Higgs boson. So it's very important that we tested the Higgs mechanism, but the SISO mechanism and leptogenesis could open the door to some new theory that could be related to supersymmetry and more particularly also to grand unification, or maybe some new symmetry that we have yet to be discovered. So I think in the next years, the kind of experiments that we have been discussing in these days here could be really mark a completely new horizon, a completely new field, and so they could open the doors to a really new kind of physics that we have been speculating so far, but now it's probably we have the tools to discover it.
You have mentioned supersymmetry, and just to follow your road you just marked, is it important to have some indication from LHC for supersymmetry, or you just keep it for higher?
I would say that it's not directly important from the point of view of leptogenesis and the explanation of the matter-antimatter asymmetry puzzle. Let's say that they are orthogonal. However, once you explain the matter-antimatter asymmetry, you would like also to explain the other cosmological puzzles, such like the dark matter puzzle, in a unified picture. And from that point of view, supersymmetry might help, or maybe this new theory that it could emerge could offer us new opportunities. So there are many new ideas now that are emerging. So it's, I think, especially for a PhD student, for example, in this moment, it's a very exciting period because we are really entering. We closed the door with the Higgs boson, with the standard model, but we are entering a completely new field, and so it's very, very, very exciting, I think.
So, and you both would like to recommend young people to think about particle physics and cosmology, and just to prepare?
Definitely.
No, definitely. I think it's very important. Actually, may add one thing about the Higgs discovery, because this set a real new breakthrough, because this is the first time ever that a scalar particle is discovered. And this is actually very important because up to now we didn't know if scalar particles exist. And one of the mechanisms which is actually driving one of the important parts of the cosmological evolution is inflation. And the basic understanding is using this is derived through a scalar field. And the second point is dark energy. Again, dark energy in accelerated expansion of the universe, and the basic mechanism which typically people think about, either it is a cosmological constant or it's driven by a scalar field. So we know now the scalar field exists. And also there were already many possibilities for dark matter candidates which are scalar fields. So at least now we have fixed a new point which is actually a breakthrough in physics. We know that scalar fields exist in nature. So
the physics of scalar fields just is opening now. Yeah?
Well, yeah. At least for fundamental scalar fields it is. So
okay, thank you very much.
Thanks to you.
It's a great honor for us that you are present here and that you participate in the conference and have already present very exciting, very important and interesting presentations. Thank you.
Thanks to you.
Thank you. It is a great pleasure for us, Professor Maury Goodman. You just come from the famous Ergon National Laboratory and present a spectacular talk on the very first day of the Lomonosov conference here, entitled Neutrino Physics in the year 2020. And really, what are the perspectives of the field to the year 2020, even beyond?
Right, well, that's very kind of you. Well, the important thing in my mind about neutrino physics is that we have a number of questions that we know have answers, that we think we can answer in a range of upcoming experiments. So I think the ones that will be answered probably by 2020 is what the overall mass scale of the neutrinos are, what the mass hierarchy is, and which quadrant the parameter theta 2,3 is, whether it's a little more than 45 degrees or a little less than 45. That'll leave some very important answers for the neutrino program of 2020 to still deal with. And the important ones are whether the neutrino is a Dirac or Majorana particle, and something about the value of the CP violation, in particular the parameter delta. All we know about it now is it's between 0 and 2 pi.
Okay. Well, thank you very much for being here, and I wish you success, and I wish you to manage to fulfill this program you just mentioned for the year 2020.
Well, thank you very much. It's been my pleasure.
Yeah, thank you. Professor Nelson, thank you very much for your very exciting, very interesting presentation you have just made on the morning session of Lomonosov Conference, and you review on really exciting possibilities that are now opening with the new facility, FAIR facility that is now under construction in the studies of fundamental properties of matter.
Yes.
May I ask you what frontiers will be opened with measurements of different masses in your experiments?
Well, the nuclear mass is a very, very fundamental property of the nuclear system, of course, and it relates to the binding energy, it relates to the Q values in all reactions, in decay, in astrophysical processes like the ARC process or neutrino-driven processes. But, and of course, it's a summary of all the properties of the mesoscopic system that is an atomic nucleus. All the binding energies comes from the combined wave function, of course. And one can then ask oneself, why do we want to measure also masses at very high isospin, very far from the nuclear stability? And there are many reasons for this, and a lot of things that will be available with FAIR, because we will be able to produce very, very exotic nuclei at high isospin with a large excess of neutrons or large excess of protons. And we will do that with a synchrotron-based facility. So we can put these very exotic species, single ions, into a storage ring and measure directly the revolution time, and by that get a handle on the mass. So that means we don't need to project with theory what the Q values are for instance, the ER process, but we can really measure in the nuclei that are in the path of the R process, for instance.
Well, thank you. It's really exciting possibilities, and let me wish you success in this field.
Thank you very much.
Thank you.
Thank you very much for a nice conference.
Thank you very much. Professor Battiston, thank you very much for your exciting presentation at the 16th Lomonosov Conference. And I would like to ask you, as a deputy spokesman of the IMS collaboration, could you, for sure, this is the most exciting and important experiment ever been produced on orbit. Could you say a few words about the history, how this experiment was designed and start operating, on the present status and the results have been obtained, and also about the future and the prospects of this experiment?
Thank you. Thank you for organizing this conference. AMS started in 1994. A team of scientists led by Professor Sam Ting from MIT and CERN decided to look to the universe to search for answers to fundamental questions which are normally searched for at the accelerator. At that time we were operating the L3 experiment at the lab at CERN. After evaluating the various possibilities, we decided to go for an experiment in cosmic rays using a magnetic spectrometer, but increasing the sensitivity and the accuracy of the measurement by order of magnitude, because we think that the cosmos, the cosmic rays and the radiation from the cosmos can still provide very important discoveries, as was at the beginning, in the first half of the last century. The history of AMS is a long one, starting in 1994. In 1998, we already flown the precursor flight of AMS on a shuttle flight of 12 days of duration, and that already gave us confidence that we can do this kind of experiment, and then we spent the remaining 15 years constructing the final configuration. It's like a LHC type of experiment. It's like a CMS or Atlas scaled down to 8 tons, which is
small by CERN standard, but extremely large by space standard. And this was operated on the International Space Station, which is the only infrastructure available in space for such large detector. The last 2 years since the launch in 2011 provided nearly 30 billion of cosmic ray data of the highest precision, accuracy. They are clean data, which we now started to revisiting the entire field of cosmic rays for from fraction AGV to a several TeV, because accuracies of the order of 1% were not available before, because balloons only fly for short amount of time, and the previous spectrometer in space, like the very good experiment PAMILA, are about 300 times smaller.
What is the total weight of these?
The total weight of AMS is about 8 tons.
8 tons. Oh,
and has about half square meters per radian of acceptance. So it's really a step forward in this direction. Indeed, it's quite interesting to know that immediately after we were able to master all the calibration and understanding all the data, because it's the first time such an experiment operates in space on the International Space Station. Immediately after we got the first result, the precision result, which indicate either new effect or correction to previously found phenomena. For example, so we are for the first time able to see a change in the slope of the positron to electron rise at high energy, which show that this phenomena, whatever it is, either a pulsar or dark matter, is reaching a maximum and hopefully will start to change the curvature and to go down, and then will be easier for us to understand which is the cause for that. Or very precise measurement of proton and helium spectra do not suggest breaking the spectrum, as was mentioned by earlier experiment, and creating a tension between the precision low energy data and the data at high energy, which is taken with different instruments and different systematic error. So basically, as a synthesis, in this first phase of AMS data analysis, we are resetting the reference spectra and plots in order to be able to exploit possible anomalies to a scale of accuracy which were not available before, anomalies which may bring to new physics. On accelerators, you control the particle beam very precisely. And you are mastering all the detail of the phenomena. In space, there are no beams controlled by man. They are provided by nature. The ingenuity of the scientists is to find ways to understand the background very, very well, and then finding out whatever remains. And this is what we are going to do for the next years.
You just recall me the words of Vitaly Ginzburg. He once said that in astrophysics, 1 is equal to 10. It seems with your exciting experiment, we just enter a new frontier of precision astroparticle and astrophysical measurements on orbit.
Absolutely correct. Something like that has happened in the last 20 years for the cosmic microwave background studies. We went from very vague phenomena, which were nevertheless extremely important, to now a very precise understanding of the tiny details which tell us about the origin of the universe. With cosmic rays, we are following a similar path. Also on gamma and X-rays, the improvement has been dramatic. Think to the Fermi experiment as an example. With charged cosmic rays, we are going to be the reference and trying to exactly do what you just mentioned, precision experiment in cosmic rays.
And for how long time you're supposed to be in orbit, just in general?
The experiment is designed to be able to cope with up to 20 years of operation. Everything depends on the space station lifetime. As you know, the agreement, the international agreement, is to operate until 2020. So we will have 7 years of operation. But there are good reasons to believe that there will be effort to extend the lifetime to 2028 at least. after having invested nearly $100 billion for such an infrastructure, you will think not twice, but 10 times before stopping it. So, and I think we are going to benefit about that.
Sure. This is a good chance for you just to be for many years.
If you want to achieve precision measurement and exploit precision measurement, you need a lot of statistics, and this will be a
So let me wish success in your very important studies of fundamentals of nature, and thank you for coming for the
Thank you
conference.
for organizing this beautiful conference.
Thank
It was
you
really a
very
pleasure.
much. Viktor Anatolyevich, it is a great pleasure for us that you are participating in the 16th Lomonosov conference, and you just welcome participants and open the conference. The point is that after the Higgs discovery, neutrinos become the priorities in some sense to neutrino physics, and we know that your institution, the Joint Institute for Nuclear Research, are paying much attention to the development in neutrino physics.
First of all, I would like to say that the conference is opened exactly in the day of birthday of Bruno Pontecorvo, because exactly 100 years ago, as such a day, 22nd of August, Bruno Pontecorvo was born in Pisa in Italy, but from 50s he worked in Russia, in Soviet Union, in Joint Institute for Nuclear Research, and I think we may say now very definitely that his talent, his genius of physicist, flourished in a full scale in Dubna. So here he suggested measure his ideas about neutrino properties and neutrino oscillations, which now under study of all the world. So, and it's very interesting to see the program of Lomonosov conference, which is very closely connected with the legacy of Bruno Pontecorvo. And I think we must be very proud that such a great discoveries are connected with the work done in Dubna, in the territory of Russian Federation, Russia, and concerning the Higgs boson. Of course, Higgs boson is a great discovery, which is crowned the success of Standard Model, which is, I think, the biggest intellectual achievements of mankind, let's say, of our days. So, but neutrino physics goes somehow beyond the Standard Model. So it's really says us that in fact the real theory is much more complicated, because work much more complicated than just standard theory speaks. But to be honest, I would say that not only these authors who suggested exactly the formula for the Higgs boson in the theory, but the very important idea of spontaneous symmetry breaking played a very important role. And we have to remind Bogolyubov Nikolai Nikolaevich, who was one of the great lecturers of this faculty, physics faculty, who, as Abdul Salam stressed always, so Nikolai Nikolaevich Bogolyubov helped to transfer idea of spontaneous symmetry breaking from the condensed matter physics to particle physics. So in that sense, Moscow State University and its physical faculty also played a very important role in establishment of success of standard theory. Like Slavnovkus you mentioned in your open speech. So this conference is really celebrates, let's say, great success of fundamental physics, and neutrino physics and standard model physics is two, let's say, cornerstones of this achievement.
And we are also very proud that Bruno Pontecorvo also was a staff member of our faculty for 20 years. He was the head of Department of Particle Physics, and so also he had a permanent position in Dubna. But also
and this 80 years anniversary of faculty, it's a dear date for many of people working in Dubna, because they were graduated here, received their way to the big science. So we wish great success to the faculty and Bruno Pontecorvo Laboratory on neutrino physics and astrophysics, so which you...
thank you very much, and we hope for a further fruitful collaboration between our institutions, the Moscow University, our group, and with your institution, with the Joint Institute for Nuclear Research. It is very important for us to have these very optimistic perspectives for the future. Thank you very much.
Thank you.
Thank you. Thank you. Thank you. we know that neutrino physics has been always a chain of problems, anomalies and paradoxes. And just a new neutrino accelerator anomaly just have been observed recently. You as Professor Thierry Lazare, you know, you are one of the best experts in the field. Could you please comment what it is, this anomaly, and what could be the way out?
Yes. So reactors, nuclear reactors, are copious producer of electron antineutrinos. They have been used for 50 years from the discovery of the neutrinos in 1956. And in the course of the preparation of the double show experiment, we try to understand the flux of antineutrinos coming from reactor to improve our knowledge on the number of antineutrinos we would expect in our detector. These reactor antineutrinos are emitted by the decay, the beta decay of the fission products of uranium and plutonium. And it turns out that in 2011, after several years of work, we could not improve the prediction. Yeah. We could not reduce the error bars. However, we found something surprising, that the previous prediction, that was a benchmark for more than 25 years, was biased, and that indeed now we know that reactors emit something like 3.5% more antineutrinos than expected before. So then we tried to understand if it would have an impact on neutrino physics. And then we reanalyzed all the past reactor neutrino experiments done at short baseline. So there are about 20 experiments that were done during the 80s and the 90s. And when doing that, we realized that not only we have more antineutrinos emitted, but we should also correct some parameters for the detection, like the cross-section that changed in the course of the last 30 years. And now it turns out that when doing that, we can compare the number of antineutrinos detected by this experiment with the new prediction, and the deficit for all the experiments, there is a common deficit, and it's about 7% less antineutrinos observed than expected, and the chance that it would be a statistical fluctuation is less than 1%. So this is what we have called the reactor anomaly, and we have to understand this effect, because we know that in the past, as you said, we had other anomalies in neutrino physics. We had less neutrinos observed with respect to expected from the sun. Yeah. This was the solar anomaly, and this can be explained by the solar neutrino oscillation. We had also less antineutrinos, neutrinos detected from atmospheric. Yeah. And this was also an anomaly, and it turns out to be another oscillation. So we have two oscillations for 3 neutrinos. And now we have another anomaly, and the question is it an artifact, experimental artifact? That could be, or is it a real effect, a real physical effect? And this is what we have to understand now in the next 10 years.
And what you could term as the most probable way out? What is your guess? Just proposal?
Yeah, I have no guess. But I think we have really we need really new input, new experimental data to show that this is a real effect or not. Because if it is a real effect, this could be a major discovery, because it could be explained by the existence of a fourth type of neutrino. A neutrino that would not interact with ordinary matter, so even more difficult to detect with respect to the other 3 neutrinos, and it would be maybe the fourth most abundant matter particle in the universe. So it would be really a major breakthrough for physics that would have implication in particle physics, in astrophysics, and also in cosmology. So it is really now a duty for the experimentalist to find out whether we have a real physical effect or not.
So we can say that really neutrinos always serve, and even now think about the futures will serve as a window to new physics. Yeah, is it true?
It's true because we know that now that neutrinos, they have a finite but very small mass that is not described by the standard model, so it is already beyond the standard model. And we know also that neutrinos, they play a role in microphysics, and they are very interesting to understand this physics beyond the standard model, but they also play a very important role in cosmology from the first second after the Big Bang in the universe. So neutrinos, they provide a window for infinity small world, and for also the cosmos as a whole.
Also, the problem you just discussed seems very complicated. Nevertheless, I wish you success in this field and to find the solution as soon as possible.
Thank you. Most important would be to find the right solution.
Thank you. Yeah, thank you. Good morning, Professor Schrock.
Good morning, Alexander.
Well, you are the world-famous expert in quantum field theory, and
try to be.
Yeah, and you are the first who considered neutrino electromagnetic properties, and your papers on this problem are, I should say, the most frequently referred papers in the theory of neutrinos. And I would like to ask you two questions. How did you first become interested in loop calculations of neutrino electromagnetic properties?
Okay, so actually in the summer of 1973, when I was a graduate student at Princeton, the first paper that I wrote was a one-loop induced decay of a neutral heavy lepton to a neutrino and a photon. Then, a few years later, in 1977, I was one of a number of people who were interested in one-loop induced electromagnetic decays of leptons to lighter leptons and photons. These included, for example, mu to E gamma. Also, nu I goes to nu J gamma, where nu J is lighter than nu I. That later led to, so those of course are transition electromagnetic moment interactions. Later, I wrote a paper with Fujikawa in 1980 where we considered the diagonal moment, the magnetic moment of the neutrino. We calculated that. It's, of course, very small, but that's part of what makes it very interesting to look for it nowadays, because it's 3 times 10 to the minus 19 Bohr magnetons times m nu over eV. And indeed, that prediction is very small for a Dirac neutrino. But the searches are especially interesting because if they find something, these include, for example, the Russian search Gamma and others, if they find something that's extremely interesting physics beyond even the standard model extended to include massive neutrinos. Of course, if neutrinos are Mariana particles, they don't have diagonal magnetic or electric dipole moments, but they do have transition moments, and those are also interesting. Another thing that's interesting that we did was the electric dipole moment. A CP violation is perfectly possible and in leptonic mixing, and there can be also neutrino electric dipole moments. Also, I've been interested more generally in neutrino masses and mixing for many years. One of the things I did in 1980 was to propose looking for massive neutrino emission via mixing in particle and nuclear decays. And those searches still go on. And so the entire area of neutrino masses, lepton mixing, and neutrino electromagnetic properties remains an extremely interesting area, partly because it certainly is the first confirmed physics beyond the standard model. But even more than that, it gives us a guide to what might lie way beyond the standard model. For example, the lightness of neutrinos but via the seesaw mechanism may indicate the presence of very high mass scales. So I think it's a very exciting subject. I'm very grateful to you for organizing this conference, Alexander, and it's a very, very good conference, and the new results reported at this conference, I think, are very important and interesting.
Well,
so thank you.
We are really proud that you have just presented your talk at this Lomonosov conference that was opened on the 22nd of August 2013 when we celebrate centenary since the birth of Bruno Pontecorvo.
I should have mentioned, absolutely, that's right.
Bruno Pontecorvo was the first who considered mixing of massive neutrinos.
Exactly.
And my question is, the second is, can you describe some of your works on neutrino masses and lepton mixing in addition to your results on neutrino electromagnetic properties?
So that, of course, and you're absolutely right, this is very fitting to honor the work of Pontecorvo. We can only wish he could have lived to see how important his work was. And so indeed, as I mentioned, one of the works that I did in 1980 was a proposal to search for massive neutrino emission via mixing in particle and nuclear decays. Those have led to extremely good, very stringent limits on the mixing matrix coefficients, which would modulate the emission of such massive neutrinos in pi L2 decay. That's pi plus goes to, say, mu plus nu heavy, or pi plus goes to E plus nu heavy. Same thing for K plus. In fact, we heard a talk here by Duke about Na62. I know that Kudenko is also planning to do this with experiment 949 at Brookhaven. And we also have heard about recent results looking for in tritium beta decay, away from the endpoint, for the emission of massive neutrinos. And so this is also, I think, a very interesting subject. And again, it's a great honor to be here, especially since it was indeed Pontecorvo who was a very great pioneer in this area.
So, and I would like to wish you success in your very important work on the field of neutrino theory. And we are, my group and myself, are also very interested in neutrino electromagnetic properties.
I know.
And we hope for future collaboration.
Absolutely, absolutely.
Very fruitful and very important for us.
Yes, I look forward to that, and I'm very interested in your work.
Thank you
very much.
Thank you.
Okay, thank you.
Okay. Academician Starobinsky, first of all, I would like to congratulate you for the Gruber Prize that you have just recently awarded.
Thank you.
And really, it is a great honor for us that you are participating in the 16th Lomonosov Conference and just have presented a talk on the round table on neutrinos, devoted to sterile neutrinos and cosmology. And may I ask you a question? And what we can learn about neutrinos from the interplay between the terrestrial experiments and cosmology?
Indeed, I expect that soon cosmology may become very useful for ground neutrino experiments, because due to tremendous progress in the accuracy of cosmological data. In particular, even if we are considered the most standard neutrino models with three generations and large difference between neutrino masses, when it follows from the ground experiments that were lowest limit on the rest mass of the heaviest neutrino of the order of 0.05 of electron volts, and expected accuracy of cosmological data is such that we can indeed expect that in the few, say, 5 years, it would be possible to achieve this value from above now, and so actually measure the mass of the heaviest neutrino. But even more interesting possibilities are may arise if indeed some hints, still hints from ground experiments about the existence of the fourth neutrino species, that with a mass of 1 electron to volt will be confirmed. In this case, it appears that to accommodate this fourth neutrinos with such a sufficiently large mass, we should have to change Einstein gravity and introduce, instead of using a cosmological constant introduced by Einstein for description of the dark energy which produces the present acceleration of the universe, then instead of this we have to use some more complicated figure. Indeed, we already have some working models, and once more, though we cannot prove using only cosmological data, they are not sufficiently exact to discover this fourth neutrino species independently. But once more, if it will be found in ground experiments, then it would be a very strong argument to change the law of gravity.
Well, and within recently confirmed non-zero Theta-13, a possibility appears to find and to search for CP population in on-ground experiments. And let's suppose that once in the near future these effects will be observed here on the Earth, what impact it could be for the cosmology?
Well, for cosmology, this effect has less clear impact, because once more, what is important for cosmology, what is important is only the total energy densities. And for them, this small effect connected with CP violation are not important. CP violation is very important for the theories of baryogenesis in the early universe, but that this requires finding a relation between the effects that you mentioned, which occurs at small energies, but for baryogenesis we are interested in the CP violation at very large energies. So I would say that this is still rather independent topics.
Well, thank you very much. Thank you very much, and I wish you success in your very important studies in cosmology. Thank you.
Thank you too.
Professor Malik from Imperial College of London has just reported newly announced results on appearance of electroneutrinos in the bunch of muon neutrinos in T2K experiment. Could you please comment on these fantastic results?
Well, certainly. Thank you very much. So I'm very excited about this result. It's effectively what the experiment was designed to do, and we were thinking we would take a very long time to get there. And with only 8% of our total data set, we've now seen a well beyond the 5 sigma potential for discovery. We've seen 7.5 sigma signal. With a background of only 4.6 events, we've detected 28 signal events, which are new E events coming out of a new mu beam. And this is really the first time that this oscillation channel has been directly observed. It's not a disappearance measurement where perhaps you don't understand your signal well enough. There shouldn't be more than a very small fraction of electron neutrinos in this beam, and we're seeing something 7.5 sigma above the background.
Well, it is really key results that have been recently announced in the biggest European high-energy conference in Stockholm, and now you just showed these results at the Lomonosov conference that is dedicated to the centenaries in birth of Bruno Pontecorvo, and it is very exciting that just you celebrate the birth of Mr. Neutrino in such a very spectacular way. Thank you very much.
Well, thank you for inviting me. It's been a pleasure. Thank you.
Thank you. Bye. Professor Wang, you are the leader of the Taxona collaboration. I would like to ask you, what is the future of your collaboration?
Yeah, our collaboration would continue working in our Huoxing reactor neutrino laboratory in Taiwan. We would be doing research using on very low energy germanium detector. The threshold we hope to get down to 100 eV threshold. That is a very low threshold for this kind of experiment. With such a detector, we would like to further improve on the neutrino magnetic moment sensitivity, and also to observe neutrino nucleus coherent scattering for the first time. And with with the same detector technology, we would like to also evolve into doing light dark matter surges. And for the dark matter surges, we would be installing the experiment with our collaborators in China, and installed it in a new underground laboratory in Western China in Sichuan province, which is the deepest operating underground laboratory in the world. So we would also like to move from neutrino physics to also to do dark matter surges.
Well, I would like to thank you for attending the 16th Lomonosov Conference on Magnetic Particle Physics, and a very important contribution that you've done during your presentation on the recent results and future project prospects of your Taxona collaboration.
Yeah.
Thank you.
I also would like to thank you as the organizer very much. I thoroughly enjoyed this conference, and it's a very stimulating environment, and I would very much like to come back in some future occasions. Okay. Thank you very much.
Thank you.
Thank you.
Dr. Andrei Tikhonov from Ljubljana University is the member of Atlas collaboration in CERN. Andrei Tikhonov presented a talk at the 16th Lomonosov Conference on exotic searches at LHC. Well, could you please comment on what is exotic and what you suppose to observe in your searches?
First of all, exotics is everything, any phenomena beyond the standard model, except for supersymmetry. So, for example, the notorious black holes falls in this category. So, well, I would not say it's too exotic, because it's the manifestation of one of the most famous extensions of standard model, extra dimensions. So if there are indeed some extra dimensions, we should see them, for example, through the production of microscopic black holes at LHC. But it's just one of the possible options. There are a few different models. Of course, the supersymmetry is the most obvious candidate for the physics beyond the standard model. But for example, there are models like vector-like quarks, or like models of neutrino masses, which is especially interesting for you at your conference, like seesaw mechanisms, which we also manifestation of these models will look at our exotics analysis. So, and I myself, I'm involved in the dark matter searches with Atlas. Yes.
So this, in some sense, it is complementary to dark searches at reactor neutrino experiments?
Yes, because indeed it's the complementary analysis. For example, I myself, I'm looking for the so-called lepton jet models, which can be seen either in the proton-proton collisions at colliders or via the cosmic rays. So yes, indeed, it's the complementary research.
Well, thank you very much, and I wish you success in your studies.
Yeah, thank you for inviting me to this conference.
Professor Carlo Giunti is a famous expert in the theory of neutrinos from University Anna Fan of Turin. And I would like to ask you, what is the present status of sterile neutrinos?
Well, sterile neutrinos are, from the theoretical point of view, are very interesting particles because they can give us indication of some physics beyond the standard model. And so people scientists are very interested in this topic, and they are looking for possibilities to see the existence of sterile neutrinos through the oscillations between active and sterile neutrinos. And the oscillations are due to the fact that the neutrinos have mass, and these oscillations can be observed in some special experiments like reactor experiments, and also experiments with some radioactive source, which is a powerful source of neutrino. And one can see them by putting a detector very close to these sources. And at present there are some indication in favor of the existence of these neutrinos. But new experiments must check better if these indications are correct or not.
Well, just recently we are observing the rapid progress in neutrino physics, both in theory and experiment. And if really sterile neutrinos exist, what is your expectation? When they can be observed experimentally? When, I mean?
Rather soon. There are some experiments which will look at the oscillations which are generated by these neutrinos. And since they have a large detector, they can see inside the detector the probability of detections of the neutrino, which depend on the distance. And this will be a clear signature of the existence of sterile neutrinos.
Okay, thank you once again. And so we have some joint projects for studies of neutrino electromagnetic properties, and I very much hope that we shall continue this research, and well, I wish you success in the field.
Thank you very much.
John Bleimeyer, the foremost expert in the theory of jurisprudence, the author of more than 200 treatises in the field, the former fellow of the Matthew College of the Princeton University, has always participated in the intelligentsia meeting that have been organized within the Lomonosov Conference since 1995. And just an hour before, John Bleimeyer gave a spectacular presentation on the problem of intelligentsia. And I would like to ask you a question, very short and very simple. What is the future of intelligentsia?
Well, my view on the future of the intelligentsia is very optimistic. And the reason is very simple. You see, the future belongs to those who are well qualified, those who are competent, those who are intelligent. And that's precisely the members of the intelligentsia. People who spend time thinking deeply about the problems that they face and analyzing them. People who are creative. Those are the people who can survive in difficult times. The people who are looking at things superficially and who do not have a thorough understanding of the world around them, those are the people who are in greatest danger and unable to survive in difficult, trying times. We're living in trying times, and these are precisely the times which require the skills of the intelligentsia to help others, but also the people who have those skills will be able to survive on their own. So that I believe that in the long term, that the intelligentsia will prosper, will thrive, and will become a larger percentage of the population over time. And of course this is our objective, because in a society where the majority of the people are genuinely intellectually engaged and thoughtful, those are the same people who are going to observe the golden rule in relation to one another, who will do unto others as they would have others do unto them, and who will therefore build a better, just, and a bright future for mankind.
Well, you just really show very optimistic perspective for intelligentsia, and you just bring hope for people who might thought to belong to this very narrow, really, society, be optimistic. And let's hope that the representative of intelligentsia will manage to survive to the next edition of the Lomonosov Conference that will be held in 2015. And let's hope that we shall continue this discussion on the problems and future of intelligentsia.
Very good. Let's raise our glasses for that.
Yeah, thank you.
Okay, thank you.